All right, guys, welcome back to our ongoing discussion of the TCA cycle. So we've sort of covered the setup of where we're going, sort of a big picture sense. So now it's sort of time to dive right on in. So right here at the top, the very first reaction of the TCA cycle. This is also what I referred to last time as sort of what I think of as sort of phase one of the cycle. You'll see why. What's essentially a single reaction, I sort of refer to as phase one because this is a little involved, right? Okay, so let's just write this out, right? So the reaction we're basically talking about here, if you remember, we ended glycolysis with formation of this alpha keto acid pyruvate, right? And the first thing we need to do is to prep this what's essentially going to be a 2-carbon unit for entry into the main cycle of the TCA cycle. And that's going to involve taking some NADH, some NAD plus, and some reduced coenzyme A, right? And using these guys to create a decarboxylated, or to drive a decarboxylation reaction in which we thioesterify that pyruvate carbonyl carbon to form acetyl-CoA, right? Plus CO2 plus NADH, right? So essentially what we're running here is an oxidative decarboxylation reaction, right? So that carboxylate group is going to get driven off as gaseous CO2, essentially, right? And we're going to power that decarboxylation, or use that decarboxylation reaction to power formation of this acetyl-CoA group. And remember, as we talked about before, this basically becomes this activated 2-carbon carrier, right? This acetyl group in that thioester bond is this activated carrier of that 2-carbon unit, which you're subsequently going to use to synthesize citrate in the next phase of the beginning of the next phase of the cycle, right? But what we want to understand now is how this works. Well, the enzyme in the simplest terms that would drive this reaction is sometimes known as pyruvate dehydrogenase. Or sometimes PDH, right? Now, the simply naming it pyruvate dehydrogenase, or the simplicity with which I was able to just write that down, belies what's really going on here, right? This reaction actually doesn't involve one enzyme, it involves 3, right? There are 3 different enzymes that are responsible for making this reaction go, so-called E1, an E2, and an E3 enzyme, right? And all 3 of these enzymes that represent the pyruvate dehydrogenase reaction are present in one gigantic supercomplex, sometimes known as the pyruvate dehydrogenase complex, right? So more correctly, this would probably be called, instead of just pyruvate dehydrogenase, would be the PDH complex. We'll look at that in a minute, right? Okay. In addition to the fact there are 3 enzymes, there are 5 cofactors. Enzyme 1 requires a cofactor we just saw when we talked about fermentation reactions, thymine pyrophosphate. Enzyme 2 requires 2 cofactors, essentially. Well, one's really sort of a substrate, but it requires this cofactor known as lipoamide, right? And then reduced CoA. Right? The E3 enzyme requires reduced FAD and NAD plus, right? So there are essentially 5 cofactors that go into this reaction for 3 different enzymes, right? And essentially what we're gonna run here is an irreversible reaction. Like I said, this oxidative decarboxylation is irreversible. Once this reaction goes, it runs pretty efficiently. Again, I don't have the free energy off the numbers off the top of my head, but the delta G naught prime for this reaction is significantly less than 0, right? Because of this release of gaseous CO2 is quite energetically favorable the way this reaction ends up being run. Okay, so what are these enzymes, right? There's E1, E2, E3 enzymes, right? So the E1 enzyme is the one that actually gets the real moniker pyruvate dehydrogenase, right? This is the enzyme that, like I said, that uses TPP, and on the front end is going to run a reaction very similar to the pyruvate decarboxylase reaction we saw that yeast run at the front end of their alcoholic fermentation reaction, that first step of alcoholic fermentation. Pyruvate dehydrogenase, the E1 enzyme, is going to run a very similar reaction, but this complex doesn't just turn around and make acetaldehyde and then, like, you know, stuff electrons back into it. We're going to use that hydroxyethyl TPP moiety to synthesize a thioester, right? The E2 enzyme is formerly known as dihydrolipoamide. Transacetylase. You'll see why in a bit. And this is the enzyme that needs both lipoamide and reduced CoA. Right? The E3 enzyme is known as dihydrolipoamide dehydrogenase. And this is the enzyme that needs both FAD and NAD plus to function. Okay. Now, the reaction here, even though I've written down 3 enzymes, it actually takes 4 steps. There's sort of 4 discrete steps to this reaction, right? And as I said before, this is going to involve an enormous multi-enzyme complex, right? And just sort of give you a sort of reference, you guys here. So the pyruvate dehydrogenase complex is huge, right? This complex, the prokaryotic PDH complex is something like 5 megadaltons in mass. The eukaryotic PDH is in the range of 9 megadaltons, right? Just for reference, right? If you guys don't remember, a prokaryotic ribosome is in the range of about 3 megadaltons, right? Whereas a eukaryotic ribosome is in the range of 4 megadaltons, right? So this complex, this PDH complex, this pyruvate dehydrogenase complex, is twice the size of one of the biggest macromolecular machines that you guys have probably been exposed to. This thing is twice as big as a ribosome, right? And it's basically what you're going to see is a little nanofactory, right? That's running a little sequenced robotic-like reaction to synthesize acetyl-CoA, right? Okay. So let me do something here. Oh, I've got this thing there. Okay, there it goes. I wanted to make that. All right, let's look at this again. All right, so this is sort of what the outside of this complex looks like, or this is an intact PDH complex. I think this is a prokaryotic. I'm pretty sure this is a prokaryotic complex. And as far as I know, the full atomic structure of an assembled PDH complex has not been solved to date. It's a really challenging problem. These things are really, really big, right? And like I said, the prokaryotic complex is already 5 megadaltons. The eukaryotic is 9 megadaltons. That's hard for even things like cryo-EM to handle well, especially when the level of heterogeneity that can exist on the inside of this complex. So, but we've got structures of these complexes at sort of lowish resolution, like the one here, 10, 20 angstrom resolution. And there are crystal structures of all the intervening components, or most of them anyway, or not quite all the pieces, but most of them. So we got a pretty good idea of how this thing is put together, right? The reason the eukaryotic complex is so much bigger is, in addition to the core catalytic components, the eukaryotic complex, at least the liver version of this complex, has is elaborately regulated, and it's got all these regulatory subunits, kinase and phosphatase domains that are layered on top of this thing that let it be regulated in a really sophisticated way. We'll talk about that a little bit later. So what you're looking at here is the sort of outer shell of the PDH complex, right? And what is visible here on this outer shell, these are the E1 enzymes. Those are the pyruvate dehydrogenase enzymes, right? So now if you drill down into this structure, what you see is sort of the next level is shown here kind of in green, right? These are the E3 enzymes, right? That's the dihydrolipoamide dehydrogenase. And as you go down a level even lower, here shown in this sort of red kidney bean sort of shape, that's the E2. Those are the, right down in the core, those are the transacetylase enzymes. So in another view of it, looks something like this, sort of schematized. And what you'll notice is each one of those subunits, right? Where each one of these is sort of like a dehydrogenase subunit, or the green one there is a pyruvate dehydrogenase here, or the green one is the dihydrolipoamide dehydrogenase, and down there in the red that's the transacetylase. Each one of those balls is a multimer. Each one of these E1s is an alpha 2 beta 2 heterotetramer. The dihydrolipoamide, the E3s, the dihydrolipoamide dehydrogenase E3s, it's an alpha beta heterodimer, and the E2, the transacetylase down in the core there, it's a homotrimer, right? Okay, so this is a big complex machine that is going to be used in a very specific way to drive this set of 4 reaction steps from pyruvate through this decarboxylation to form acetyl-CoA. And we'll look at the mechanism in the next video.